Hello, my name is Nima Mirhadi. I am a PhD student at the University of Alberta, and my today presentation is about the weather signature for recurrent instabilities near Drumheller, Alberta. The site that I'm working on is called CO18, which is located 12 kilometers northwest of Drumheller city along the Red Deer River Valley, and it consists of a 500-meter long, 60-meter high rock slope, which is located on a weak, poorly indurated sedimentary rock with layers of stronger sandstone, siltstone, and coal. The slope is located adjacent to the Highway 837 and has a history of erosion on riverbank slopes, rockfalls, and soil slides. Since July 2000, 11 landslides have been recorded at this site by Alberta Transportation and KCB. The CO18 site is part of the Horseshoe Canyon Formation, which is approximately made up of 60% siltstone, 30% sandstone, and 10% coal. Some of the coal layers can be seen from this photo that was taken in November 2019. The angle of a slope of the site is about 30 degrees, and Stalker in 1973 stated that the erosion of meltwater streams and of rivers cutting new channels after diversion from their aerial valleys are the reason of emergence of these steep valleys. The first landslide was recorded in July 2000, and since then, due to the sensitivity of the subject, Alberta Transportation continued monitoring the area and recorded all landslides. Up to now, they have reported 11 landslides at this site. And according to the published reports, earth flow, slides of frozen slabs of weather material, and rockfall are three types of failures that have been identified at this site. Except one that happened in the winter of 2017 and the latest one that happened in January 2021, all other incidences have occurred during spring and summer, or more precisely between May and July. And when you look at the weather data that I'm going to show in the next slide, so you see that there is more rainfall in this month, and this shows that there should be a relationship between weather and landslide. And that's why in this research, we decided to look further and investigate the effect of weather-related influences, such as precipitation, temperature, and freeze-thaw cycles on the landslide at the CO18 site. This is a front view of the site, and the locations of the recorded landslides are shown. And as you can see, most of them have occurred in a small area close to the north end of the site. We defined a number of objectives for our research. First, we want to develop a method to quantify the change in landslide risk at a local scale as a response to weather. We also try to develop an effective notification system about high-risk periods at a local scale, and we also try to develop a decision tree that results in a failure probability by considering the geology, geometry, and weather information of the desired location. Okay, now let me show you a summary of the weather conditions. 8 closest weather stations to the site, as shown in Figure 7, were selected, and their data, including hourly and daily temperature and precipitation, were extracted from the available online databases for the period of January 2000 to December 2020. A summary of the weather conditions, including the minimum, average, and maximum values of temperature and precipitation, is provided in Figure 6. And as is shown, an average of about 170 millimeter out of annual total of 300 millimeter of rain falls in summer, or more precisely between June to August. Moreover, the average temperature was below 0 degrees Celsius from November to the following March, which is important in calculating the freeze-thaw cycles and the subsequent weathering. The study of historical climate is important not only because it helps to understand the current weather conditions, but also because it assists with the predictions of future conditions. So in this study, the historical weather data from 1955 to 2020 was collected from Alberta Climate Information System database and analyzed for this study. Results are summarized in the bottom left chart. And if you can see, while average air temperature seems to be constant with little fluctuations around some years, the total precipitation, which is shown in the bottom right chart, doesn't have the same behavior, and the linear trend line shows that the total annual precipitation has been increasing slightly since 1955. This information is used along with other available data to study how climate affects landslide activity at the CO18 site. As an example, the 4-month antecedent average daily air temperature and total daily precipitation for some of the events are shown here. On the top, the weather data for the July 2005 and June 2007 events are shown. It can be seen that in both events, the failure happened a few days after a period of rainfall. In other events that occurred in spring and summer, which are not shown here, the same conditions are seen. On the other hand, a different weather condition and failure mechanism are seen in the events that occurred in winter. For example, in the December 2017 event, which is shown on bottom left chart, the simultaneity of rainfall and sudden drop in temperature 45 days before the failure caused the water to freeze shortly after the rainfall and before the water had the chance to evaporate, penetrate deeper into the formation or run off the slope. The combination of freeze-thaw and freezing rain is believed as the reason of having landslide in a colder month at this site. In the case of December 2017 event, 20 days after the average air temperature reached around 0 degrees Celsius, a rockfall happened. In the right figures 10 and 11, the cumulative precipitation and the cumulative freeze-thaw cycles that were calculated for the periods of 3 to 90 days before each event are shown. These antecedent values have been used to calculate the possibility of happening a similar landslide. For example, table 2 states that an average of 6.9 millimeters of rainfall occurred in the previous 3 days before each failure. It also shows that a minimum of 4.4 millimeters of rainfall occurred in the previous 14 days before each event. So in order to calculate the possibilities of having a similar failure, I used the antecedent rainfall values of the May 2018 landslide to determine 3 possibilities. The first probability is the likelihood that a failure happens if the criterion is exceeded. And according to the weather data, there were 188 periods of time between January 2000 and May 2021 in which the cumulative precipitation in up to 90 days prior to that date was higher than the values of May 2018 event. And considering that 6 events occurred under these conditions, the likelihood of happening a landslide if the criterion is exceeded is 3.2%. The second one is the likelihood that a failure happens if the criterion is not exceeded, which in this case is 0.06%. And the ratio of first likelihood to the second likelihood is 53.3, which means that under this criterion, the chance of having a similar event like the May 2018 event is 53.3 times higher of not having a failure. And the third one is the rate of days when the criterion was exceeded but no failure has happened, or the rate of false alarm, which in this case is 96.8%. The main objective of this study is maximizing the first number, the first probability, and minimizing the false alarm rate, which is possible by defining more criteria and expanding the available database at the same time. In another statistical analysis, I calculated the 3 likelihoods that I mentioned in the previous slide, assuming a rainfall threshold for each time window. So for example, the point here on the left figures showed that if we have more than 10 millimeters of rain in a 7-day time period, considering all of the recorded landslides in the past 21 years, there is a 2.5% chance of happening a landslide with only a 0.09% of the likelihood that a failure happens if we have less than 10 millimeters of rain in 7 days. And again, for a 14-day time window, which is shown in the right figures, if we assume that there were more than 20 millimeters of rainfall in the last 14 days, we can say that there is a 6% chance of having a landslide in the near future. It also means that in 94% of times, it's just a false alarm and no landslide will happen. The right figure 12, the ratio of probability 1 over probability 2 is shown, and we know that the higher this ratio is, the better the defined criteria is. I mean that we are searching for a criterion that gives us a higher likelihood of possible landslides, but at the same time, we want it to give us a smaller likelihood of a possible landslide if it is not exceeded. And that's why I calculated the ratio of probability 1 over probability 2. And based on these findings, it can be seen from the figure 12 that a 10 millimeter rainfall in 7 days and a 20 millimeter rainfall in 14 days can be considered as proper threshold values for this site, considering the low number of actual available landslide data we already have. So until now, we found that except for the May 2013 event, all other 8 events that occurred in spring and summer happened shortly or a few days after a period of rainfall. And results showed that an average of 6.9 millimeters of rain has fallen in the previous 3 days. And weather data also show that at least 4.4 millimeters of rain has occurred during the 14 days before the failure. We also found that there is a direct relationship between the recorded failures and the antecedent precipitation, and it shows that the rainfall is the key triggering factor in the occurrence of failures at the CO18 site during spring and summer. We also found that there is a different failure mechanism that is involved in the events that occurred in winter. For example, in the December 2017 event, the correlation between the timing of the rainfall and the sudden drop in temperature caused the water to freeze shortly after the rainfall, and 20 days after the average air temperature reached around 0 degrees Celsius, the rockfall occurred. In winter events, freeze-thaw cycles and precipitation together play a role in the occurrence of failures. And let me talk a little bit about my next goals for this study. Since December 2017, 3 more landslides have happened at the site. And in order to investigate how the landslide has expanded to the site, a series of change detection analyses were performed on the point clouds generated from photogrammetries taken between May 2018 and May 2021. Results of the M3C2 analysis are shown in figure 13. And all changes in this figure are calculated relative to December 2017. And as it can be seen since that time, the flanks of the landslide have moved to both sides, mostly to the north, while the crowns moved higher up in the slope. In the next few months, I'm going to focus on the weather data from weather data after the December 2017 failure to see if there is any meaningful relationship between the weather and the failures happened in the last 4 years. I also am going to use historical aerial photos to find the relationship between weathering process and landslides. I will also use digital elevation models to calculate the superficial water path like the ones shown in figure 15. To find the relationship between the density and location of the water path and the visible landslides on the slope. Thank you very much for letting me share my findings with you. If you have any suggestions questions or comments, I'm happy to hear them.